By the summer of 2003, the desktop processor war appeared to have become a contest that Intel was built to win. On June 23rd, the company introduced a Pentium 4 running at 3.2 gigahertz, another step in a frequency climb that had transformed a technical specification into one of the most recognizable measures of PC performance. 3 years earlier, a 1 gigahertz processor had represented the leading edge of the consumer market. Now Intel was selling more than 3 billion clock cycles per second. Backed by the Pentium name, enormous manufacturing resources, broad support from PC makers, and a marketing message almost anyone could understand, faster clocks suggested faster computers. The logic fit neatly on a specification sheet, and for shoppers comparing machines on a store shelf, few numbers carried more immediate authority. AMD faced an awkward problem. Its processors could not simply be judged by the same arithmetic. The company had already spent years using performance ratings rather than raw frequency as the primary model number on many Athlon products, a practice that attracted criticism precisely because Intel's clock speeds were so much easier to compare. If a Pentium 4 said 3.2 GHz and an AMD processor operated somewhere near 2 GHz, the difference looked enormous before either machine had run a single program. For AMD, losing that comparison on the box mattered because Intel was not merely another competitor. It was the dominant supplier of x86 processors, and the Pentium brand had become deeply embedded in the public idea of what a powerful PC was supposed to contain. Yet behind the simple numbers, the contest was becoming harder to explain. Reviewers were already accustomed to finding that two processors with different frequencies did not always finish real workloads in the order their clocks predicted. Games, office applications, media creation, rendering, and other tasks stressed different parts of a processor and its surrounding platform. Intel itself promoted more than frequency alone, emphasizing features such as hyper-threading and faster system buses. Still, GHx remained extraordinarily visible, and the Pentium 4 architecture was designed around the ability to push that figure upward. That made what happened in September unusually uncomfortable for the conventional comparison. On September 23, 2003, AMD formally brought its K8 architecture to desktop PCs as the Athlon 64 and Athlon 64 FX. The ordinary Athlon 64 3200 Plus entered a market where Intel already had a 3.2 GHz Pentium 4. Yet early testing placed AMD's new processor in the same performance conversation despite its far lower operating frequency. The results were not a universal AMD victory. Intel remained strong in content creation and other workloads that suited the Pentium 4, and different tests produced different winners. What changed was the credibility of the shortcut itself. A customer could no longer look at a gap approaching a gigahertz and safely assume that the larger number described the faster machine. AMD's challenge, therefore, reached beyond one benchmark or one product launch. The company had arrived with a processor that forced reviewers, enthusiasts, and eventually buyers to confront an inconvenient question. If 3.2 GHz did not automatically defeat a chip running far slower, what exactly had Intel been optimizing when it built the Pentium 4 to chase frequency so aggressively? The answer reached back to a decision Intel had made before the Pentium 4 ever appeared on a store shelf. NetBurst was not designed simply to make the next processor a little faster than the Pentium 3. Intel wanted a desktop architecture with far more room to raise frequency across successive generations, and that ambition shaped the processor from the inside out. The original Pentium 4 stretched instruction processing into a pipeline of roughly 20 stages, about twice the depth Intel cited for the Pentium 3. Dividing the work into smaller steps made higher clock rates easier to achieve because each stage had less to complete before the next clock edge arrived. The attraction was obvious. If improvements in semiconductor manufacturing continued supporting faster operation, Intel could keep increasing the number of cycles available every second and refine the architecture around that growing frequency. NetBurst included mechanisms intended to keep this high-speed design productive, including a trace cache that stored already decoded micro-operations and an execution engine built to sustain very rapid integer operations. The surrounding platform was also designed for greater bandwidth. Intel was not merely chasing a large number for advertising purposes. It was engineering around the expectation that higher frequencies would remain one of the most powerful ways to increase performance. At the beginning of the decade, that expectation looked entirely reasonable. Digital video, audio processing, 3D graphics, internet media, and increasingly demanding software all appeared ready to consume whatever computing power the industry could provide. The first Pentium 4 processors arrived in November 2000 at 1.4 and 1.5 GHz. Intel moved quickly from there. Within months, the line had reached 1.7 GHz, and later revisions continued climbing. By January 2002, the Pentium 4 had reached 2.2 GHz on Intel's 0.3 micron process, accompanied by a larger L2 cache and the promise of considerably more frequency still ahead. Each milestone seemed to validate the architecture's central premise. NetBurst had been created with room to accelerate, and that room was being used. Yet frequency represented only one part of processor performance. Designing a core to sustain a faster clock inevitably required engineering trade-offs elsewhere, and those trade-offs would matter differently depending on the software running through the machine. Intel understood that problem and continued refining the architecture rather than relying on frequency alone. For the moment, however, the upward trajectory was persuasive enough that NetBurst appeared to possess exactly the future Intel had designed for it. The serious challenge would come from a competitor that was not preparing to push the same philosophy further. AMD was developing a K8 around a different judgment about where processor performance was being lost. And instead of trying to reproduce Intel's path to ever higher G8s, it was preparing to redraw parts of the architecture that the Pentium 4 had largely left in place. AMD's alternative had been taking shape long before the Athlon 64 name appeared. The company had already learned an uncomfortable lesson during the K7 era. Competing with Intel did not require matching every clock speed milestone, but selling a processor that appeared slower on paper created its own problem. Athlon processors could deliver strong real-world performance at lower frequencies, yet the market increasingly treated megahertz and then gigahertz as shorthand for speed. AMD's response was not to redesign its processors simply to produce a larger number. It began using performance ratings such as 1800 plus, 2400 plus, and eventually 3200 plus, attempting to communicate that operating frequency alone did not describe how much work the processor could complete. That choice was controversial. To critics, the model numbers looked like an attempt to disguise lower clocks. To AMD, they were a defense against a comparison that favored Intel before any application had been run. The disagreement exposed something deeper than marketing. AMD's engineers were developing K8 from a very different starting point. Instead of abandoning the strengths of the existing Athlon design in pursuit of an architecture built primarily for extreme frequency, K8 evolved the K7 foundation. Its pipeline remained comparatively moderate, and the design continued emphasizing strong execution efficiency rather than depending on enormous increases in clock rate to produce every new generation of performance. That did not mean frequency was irrelevant. AMD still needed faster transistors, improved manufacturing, larger caches, and higher operating speeds, like every other processor company. The difference lay in how much of the performance strategy depended on the clock itself. K8 was being built so that improvements elsewhere in the machine could matter just as much. This became increasingly important because by the early 2000s, the processor was no longer isolated from the rest of the system. Faster cores placed greater pressure on memory access, data movement, caches, and the connections between the CPU and the chipset. Raising frequency could make arithmetic happen sooner once the processor had the information it needed, but it could not automatically shorten every delay involved in obtaining that information. AMD's engineers therefore treated some of those delays as part of the processor problem, rather than as conditions the CPU simply had to tolerate. The company also had another constraint. It could not assume that software developers, PC manufacturers, or consumers would abandon the enormous base of existing x86 applications merely because AMD wanted to introduce a new architecture. K8 had to move the platform forward without breaking the compatibility that made x86 commercially valuable. The result was a design that looked evolutionary in some places and unusually aggressive in others. When AMD first discussed its Hammer family publicly, the project represented more than another Athlon with additional cache and a higher model number. It was an attempt to change where the boundaries of the processor itself should be drawn. That distinction would become crucial because one of the largest delays confronting a fast CPU occurred outside the execution core, along a route that desktop processors had relied on for years. AMD decided that K8 should no longer take that route. That route ran through the chipset. In a conventional Pentium 4 system, the processor did not communicate directly with the main memory. Requests traveled across the front-side bus to the chipset's memory controller, which then handled access to DRAM and returned the requested data. Intel could increase bus speed, improve chipsets, enlarge caches, and refine prefetching to reduce the impact of that journey, but the basic arrangement remained intact. AMD chose to remove one of its most important steps. K8 placed the memory controller on the processor itself, bringing control of system memory onto the processor die, rather than leaving it in the North Bridge. The change did not make DRAM suddenly operate at processor speed, nor did it eliminate the delays inherent in accessing memory. What it removed was an intermediary. When K8 missed its caches and needed information from main memory, it no longer had to send the request through an external chipset memory controller before reaching the DIMMs. That shorter path reduced latency, and contemporary testing would show just how significant the difference could become. The importance extended beyond a benchmark number. Modern processors spend enormous amounts of effort trying to keep frequently needed information close to their execution hardware, because waiting for distant data wastes opportunities to do useful work. As CPU frequencies increased, the mismatch between the speed of the processor and the speed of main memory became more painful. AMD's integrated controller attacked that problem at the system level. It also changed the role of the motherboard chipset. Memory traffic no longer depended on a Northbridge controller selected by the motherboard vendor, so one major source of platform variation moved under AMD's control. The rest of the system still needed a fast connection to the processor, and this was where HyperTransport entered the K8 design. Rather than using the old front-side bus as the shared route for both memory-related communication and the wider chipset, AMD used HyperTransport links for high-bandwidth communication between the processor and I/O logic. Memory followed its own direct path through the controller inside the CPU. The distinction mattered because K8 was not merely accelerating an existing bus. AMD had reorganized the traffic pattern around the processor. There were costs to that decision. Integrating the memory controller made the CPU more closely tied to particular memory technologies, and future changes in DRAM standards could require corresponding processor changes, rather than being absorbed only by a new chipset. It also placed additional complexity onto the processor die. AMD accepted those constraints because lower memory latency offered an advantage immediately, especially in applications that frequently reached beyond the cache. Games were particularly sensitive to such delays, but the effect was not confined to gaming. Any workload whose performance depended heavily on irregular memory access could benefit when the processor spent less time waiting for data to arrive. None of this guaranteed that Athlon 64 would beat Pentium 4. Intel still possessed tremendous frequency, strong memory bandwidth, sophisticated prefetching, SSE2 performance, and workloads that suited NetBurst extremely well. The important change was that frequency now had to compete with an architectural advantage that GHS could not describe directly. For the first time in this rivalry, AMD had altered not just how fast the processor executed instructions, but how quickly the rest of the system could feed them. The pressure became visible the moment reviewers stopped comparing labels and started comparing finished work. On paper, Intel's advantage still looked overwhelming. A 3.2 GHz Pentium 4 completed roughly 60% more clock cycles every second than a 2.0 GHz Athlon 64 3200 Plus. If frequency alone represented processor speed, there should have been little mystery about the result. Yet across many desktop and gaming tests, the gap either collapsed or reversed. Athlon 64 could finish some workloads as quickly as Intel's much higher clocked processor, and in several games, it moved clearly ahead. The reason was not a hidden multiplier or a trick in AMD's model numbers. Frequency measured how often the processor's clock advanced. It did not measure how much useful work the architecture completed during each advance. That second quantity depended on the design itself, how effectively instructions moved through the core, how often execution units remained productive, how much useful work survived speculation, and how quickly required data became available. This was where the philosophical divide between K8 and NetBurst finally became measurable. Pentium 4 had been built to reach frequencies that a shorter design would struggle to sustain. To accomplish that, Intel divided instruction processing into more stages, allowing less work to be performed between individual clock edges. The approach delivered extraordinary frequency headroom, but it also meant that a clock cycle on one architecture could not be treated as equivalent to a clock cycle on another. Branch prediction made the difference especially visible when software repeatedly forced the processor to choose between possible instruction paths. Modern CPUs try to predict which path a program will take, rather than waiting until the answer is certain. When the prediction is correct, work continues with little interruption. When it is wrong, speculative instructions already moving through the pipeline have to be discarded and the correct path restarted. A deeper pipeline can make that recovery more expensive because more unfinished work may be in flight. Intel invested heavily in prediction technology to limit the damage, and NetBurst performed extremely well when its machinery remained supplied with predictable streams of instructions. Certain media encoding, rendering, and optimized workloads demonstrated exactly why Intel's strategy could be powerful. Games and less regular desktop software often presented a different pattern. Their branches, memory behavior, and changing workloads gave K8 opportunities to exploit strong per-clock execution and its lower latency access to memory. The result made AMD's performance rating system easier to understand, even if it did not eliminate the controversy surrounding it. A customer buying an Athlon 64 3200 Plus was not purchasing a 3.2 GHz processor disguised under another name. The chip actually operated at 2.0 GHz. AMD was effectively arguing that the model number should reflect expected performance rather than raw frequency, an argument that became increasingly defensible once the processor was tested against Intel's 3.2 GHz flagship. It was also dangerous to oversimplify the outcome. Pentium 4 still won important tests, and software optimized for its strengths could produce impressive results. No single benchmark established that K8 was universally superior. What the comparison destroyed was something more basic, the assumption that the processor with the larger GHz figure must therefore be faster. Intel had spent years turning frequency into the easiest public language of CPU progress. Athlon 64 forced the industry to confront the limits of that language, just as AMD was preparing a second challenge, one that had almost nothing to do with clock speed and everything to do with who would define the future of x86 itself. That future was already taking shape inside K8. The Athlon 64 name advertised the feature directly, but AMD's 64-bit strategy mattered for a reason that went far beyond allowing a processor to handle larger numbers. By the beginning of the 2000s, mainstream x86 software still lived largely in a 32-bit world. That environment carried an important limitation. The conventional 32-bit address space restricted how much memory a single process could address directly, an issue that would become increasingly significant as workstations, servers, games, and professional applications demanded larger datasets. Moving beyond it was not simply a matter of widening registers and asking developers to start over. The PC industry was built on decades of x86 software, operating systems, drivers, and business applications whose compatibility had enormous commercial value. AMD's answer was AMD 64, originally developed under the x86 64 name. Instead of replacing x86 with an unrelated instruction set, AMD extended it. A K8 processor could run existing 32-bit x86 software while also providing a new 64-bit execution mode, wider general-purpose registers, additional registers, and a much larger address space for software designed to use them. That compatibility gave the transition an unusually practical character. A buyer did not need every application to become 64-bit on the day the hardware arrived. Existing programs could continue running, while operating system vendors and software developers adopted the expanded architecture gradually. AMD had first brought the technology to market in the Opteron server processor earlier in 2003, then carried it into consumer PCs with Athlon 64 in September. The strategic contrast with Intel was striking. Intel had invested heavily in Pentium, a separate 64-bit architecture developed with Hewlett-Packard and aimed primarily at high-end servers and technical computing. Pentium was not simply a wider Pentium, and its IA64 instruction set did not preserve native x86 execution in the same straightforward way AMD 64 did. Intel still supported its enormous x86 business through the Pentium and Xeon families, but AMD had now created a path that allowed the familiar architecture itself to grow into 64-bit computing. Adoption did not happen overnight. Most consumers in 2003 still ran 32-bit operating systems, 64-bit Windows, for AMD 64 was not yet broadly available, and much everyday software gained little immediate benefit merely from being placed on a 64-bit capable processor. The importance of AMD's decision became clearer as the ecosystem moved. Linux distributions added support. Microsoft developed 64-bit Windows for the extended x86 architecture. Software vendors gained a target that preserved compatibility with the platform they already knew. Intel eventually introduced its own compatible 64-bit extensions for mainstream x86 processors, initially under the name EM64T and later Intel 64. That development did not mean AMD had displaced Intel commercially, nor did it turn every Athlon 64 into the faster processor. It revealed something more unusual in a market Intel had long defined. The smaller rival had established an architectural direction that the dominant x86 supplier could not ignore. By then, however, Intel was still pursuing the other great promise of NetBurst. If Pentium 4 could continue climbing in frequency, the argument over efficiency might yet be overwhelmed by sheer clock speed. Prescott was supposed to push that possibility further. Prescott arrived in February 2004, carrying the burden of proving that NetBurst still had room to scale. Intel had moved the Pentium 4 to a new 90-nanometer manufacturing process, doubled the L2 cache to 1 megabyte, added new instructions, and extended the architecture so that higher frequencies remained possible. On a roadmap, the transition looked like another familiar step in semiconductor progress. Smaller transistors had repeatedly allowed the industry to fit more circuitry onto a chip and raise performance. Intel expected Prescott to continue that pattern, eventually taking the Pentium 4 beyond the frequencies reached by Northwood. The processor that reached reviewers, however, exposed a more complicated reality. Prescott's pipeline had become substantially deeper, increasing the frequency potential Intel wanted, but also making the architecture even more dependent on keeping a long sequence of work moving efficiently. Intel improved branch prediction and other mechanisms to compensate, yet the additional stages could not create useful performance on their own. Early Prescott models often needed their architectural enhancements and extra cache simply to compete with similarly clocked Northwood processors, while another characteristic became increasingly difficult to ignore: power. Shrinking the manufacturing process had not removed the electrical problems surrounding higher frequency operation. Leakage current was becoming more significant as transistors became smaller, adding power consumption, even when portions of the chip were not performing useful switching. Higher voltage and frequency demands intensified the thermal challenge. Cooling systems grew more important, motherboard power delivery had to cope with heavier loads, and the heat produced by a high-end desktop CPU became a constraint engineers could no longer treat as secondary. Prescott still shipped in enormous numbers, supported hyper-threading on many models, gained additional features over its lifetime, and remained highly competitive in workloads suited to NetBurst. The deeper problem was the direction of the architecture. Intel had built NetBurst around the expectation that frequency could continue rising far enough to justify the compromises required to reach it. Each additional step was now becoming more expensive in watts, cooling, design complexity, and diminishing performance returns. K8 sharpened that contrast because AMD remained competitive without approaching the same clock rates. Intel could still win particular tests, but another increase in frequency no longer guaranteed a proportionally larger advantage. For years, NetBurst's strongest evidence had been its momentum. 1.05 GHz became 2 GHz, then 3 GHz, and the next milestone always appeared close enough to make the strategy seem sustainable. Intel publicly committed to a 4 GHz Pentium 4, a target that would have provided a powerful symbolic answer to AMD's lower clock challenge. During 2004, that target slipped, and in October, Intel abandoned the 4 GHz desktop Pentium 4 altogether. NetBurst continued after that decision. Faster Prescott-derived processors still appeared, eventually reaching 3.8 GHz, and Intel retained several ways to improve performance within the architecture. What changed was the assumption that desktop progress could continue depending on dramatic increases in clock frequency. The physical cost had become too visible, and Intel's own roadmap now reflected it. AMD had never matched Pentium 4 at the highest frequency numbers. By late 2004, that comparison mattered less than the fact that Intel itself had stopped treating the next major GHz milestone as the clearest path forward. Once Intel removed 4 GHz from the roadmap, the argument over processor performance began changing in a more visible place: the way the industry reviewed and sold CPUs. Hardware publications had already been forced to move beyond headline frequency because Athlon 64 and Pentium 4 produced results that varied too widely from one application to another. A single clock speed comparison could no longer summarize what buyers would actually experience. Reviewers increasingly relied on broader benchmark suites, separating gaming, office software, media encoding, rendering, and other workloads, instead of presenting one specification as a verdict. The consequence was larger than another round of benchmark victories. It changed the language surrounding desktop processors. Athlon 64 developed an especially strong reputation among enthusiasts and gamers, while Pentium 4 continued to perform well in software that benefited from NetBurst's high frequency, hyper-threading, and optimized media execution. Those mixed results made a simple ranking harder to defend. A processor could lead decisively in one category and lose in another, forcing reviewers to explain architecture, workload behavior, and platform characteristics, rather than merely repeat the number printed beside GHz. Power consumption also began entering mainstream evaluations with greater urgency. Prescott made thermal behavior difficult to ignore, and publications increasingly treated heat, cooling requirements, and electrical demand as meaningful parts of a processor comparison. Performance was no longer being judged only by how quickly a benchmark completed. The cost of achieving that result mattered as well. This shift weakened one of the great advantages of frequency-based marketing: simplicity. GHz had offered consumers a single number that appeared to place every processor on the same ladder. By the middle of the decade, reviewers were effectively teaching buyers that the ladder did not exist. Clock speed still mattered, but only inside the context of a particular architecture. Cache behavior mattered, memory latency mattered, threading mattered, software optimization mattered, power increasingly mattered. The buying decision became more complicated precisely because the processors themselves had become more different. Intel remained commercially dominant and continued shipping Pentium 4 systems on a scale AMD could not match, so the change was not a market overthrow. It was a change in what counted as credible evidence. Enthusiast sites, system builders, and increasingly mainstream buyers looked toward application performance, rather than assuming that a frequency advantage settled the question in advance. AMD had benefited from that transition because K8 performed strongly in many of the workloads reviewers emphasized, but Intel was learning the same lesson from another part of its own product line. Away from the desktop, a lower frequency processor had already shown that strong performance could come from a very different balance of efficiency, pipeline design, and power consumption. That architecture would become far more important once Intel decided that the future of the desktop could no longer depend on extending NetBurst indefinitely. That different balance had already proved itself in mobile computing. Intel's Pentium M, introduced for notebooks in 2003 as part of the Centrino platform, followed a very different set of priorities from the desktop Pentium 4. Its design drew heavily from the earlier P6 lineage while incorporating newer ideas, and it had been shaped for an environment where battery life and heat imposed immediate limits. A notebook processor could not rely on rising power consumption every time more performance was needed. Pentium M therefore demonstrated inside Intel itself that strong application performance could be achieved without NetBurst's dependence on extreme clock speed. As Prescott's scaling problems became more visible, that lesson gained strategic importance. Intel continued selling Pentium 4 after the 4 GHz target disappeared, and NetBurst even expanded into dual-core desktop processors such as Pentium D. Those products helped the company respond to the industry's shift toward multiple cores, but they left the underlying efficiency problem unresolved. Additional cores could improve throughput when software used them effectively. Yet placing more NetBurst execution hardware into a desktop system made power and thermal behavior even harder to ignore. Intel's longer-term answer emerged through the Core microarchitecture. It was a new design shaped by lessons from several earlier Intel processor families, including the mobile line, and it pursued performance through a more balanced combination of execution efficiency, pipeline depth, power consumption, and multi-core capability. The language surrounding the transition showed how much had changed. Intel increasingly emphasized performance per watt, dual-core throughput, and application results rather than presenting another GHz milestone as the central proof of progress. In July 2006, the company launched Core 2 Duo desktop processors based on the new architecture. Their impact was immediate because Intel regained the initiative without returning to the frequency trajectory NetBurst had once promised. Core 2 chips often operate at lower clock speeds than the fastest Pentium 4 processors, yet delivered much stronger performance across a broad range of workloads while improving energy efficiency. The reversal carried an obvious irony. For years, AMD had been forced to explain why a lower clocked processor could still be faster. Intel was now demonstrating the same principle through its own flagship architecture. AMD was not the sole cause of this transition. Power constraints, the success of Intel's mobile designs, manufacturing realities, the growing importance of multi-core processing, and internal engineering choices all shaped the move away from NetBurst. K8 mattered because it intensified the competitive pressure at exactly the moment Intel's existing desktop strategy was becoming harder to extend. AMD had shown that a more efficient architectural balance could deliver leading desktop performance before Intel completed its own redesign. Core 2 then changed the competitive landscape again. AMD's advantage narrowed quickly, and Intel reestablished a powerful performance position. Commercial dominance had remained with Intel throughout most of the period, but the architectural lesson had become impossible to miss. The company that had once made rising clock frequency the most visible symbol of Pentium 4 progress returned to the top with processors that proved performance depended on far more than the number beside GHz. By 2006, the terms of the competition had changed permanently. Return to the comparison that framed the entire rivalry. In 2003, a Pentium 4 running at 3.2 GHz could sit beside an Athlon 64 carrying a far lower actual clock speed. And the specification sheet seemed to make the verdict obvious before either processor had executed a single application. 3 years later, that confidence had disappeared. Intel had not been defeated as a company. It remained the dominant force in the x86 market, possessed manufacturing and commercial resources AMD could not match, and continued selling processors in volumes far beyond its smaller rival. AMD's success, therefore, cannot be measured by pretending the Athlon 64 overturned Intel's business position. Nor did K8 secure permanent technical leadership. Core 2 arrived in 2006 and quickly returned Intel to a commanding performance position, demonstrating how rapidly the balance between the two companies could change. The more lasting victory occurred at the level of the argument itself. K8 had forced the industry to confront the difference between a processor that looked faster and one that actually completed work faster. AMD did not need to match Intel's highest frequency numbers to make that distinction impossible to ignore. Reviewers had to broaden their testing. Buyers learned to distrust simple clock comparisons across different architectures. Intel eventually moved its own desktop strategy toward a design philosophy that placed far greater weight on efficiency, useful work per cycle, power consumption, and overall architectural balance. That shift was not a concession produced by one competitor alone. Semiconductor physics, Intel's mobile experience, manufacturing limits, multi-core computing, and internal engineering decisions all shaped the transition. Yet AMD had demonstrated the competing idea in the market at precisely the moment NetBurst was reaching its most difficult limits. That is why declaring a single winner oversimplifies what happened. Intel won the battle of scale. Core 2 won the next major performance round. AMD won something narrower but historically important. It proved that the metric dominating the public conversation no longer described the competition accurately. The 3.2 GHz label that once seemed capable of settling the question became only one number among many. K8's legacy was not that it made clock speed irrelevant. It was that it made one lesson unavoidable. A processor cannot be judged by how fast its clock ticks until you know what the architecture accomplishes with those ticks.